All right. How you guys doing? I was like, where's that fried chicken I smell? Did you bring enough for the class to share? Yeah, I can't blame you for it, but we can all be a little jealous of lunchtime here. Okay, so welcome. Today we're going to talk about disinfection, which happens to be kind of one of my favorite topics. Probably what I've had the most experience with. Most of my research deals with disinfection in one form or the other, or relates to it, and has for most of my time as an academic. So hopefully this will be a little bit of a fun, kind of informative style course or class period today, and then next time we'll get into a little bit more of technically how do we do the math. We'll probably get a little bit into it today just to show you, connect back to some of the stuff we've talked about already. We will deal a little bit with chemistry because there's chlorine and stuff, but there's also going to be UV disinfection and some mass balance kind of stuff involved. But I'd like to start to say, how many of you have a good understanding of the difference between sterile and disinfected? Any thoughts? Do you know? I mean, it might be on the slide, I don't know. If I were to ask you, do you think this water I just got from the water fountain, you think it's disinfected? Probably, maybe. At least at some point it was disinfected, right? Who knows what I had in the bottle before, right? What about sterile? Okay, so no way. Yeah. And perhaps it's already up there, right? So you're right to say it's not sterile. I know for a fact there are organisms in there that can live and reproduce. That's kind of the definition. When you sterilize something, we use that term kind of like sterilizing a surface, but what it really means is you're making it an organism sterile, meaning to make it not be able to reproduce. So if you neuter or spay a dog, let's say you are sterilizing the dog. You could have some organisms that hybridize, but their offspring is sterile, like a donkey, for example, or a mule, rather, whichever the right one is. And essentially, you could have all sorts of pathogens in here, but if you sterilize them, they could still be living, and then I could drink it, but they can't reproduce, so they don't cause an infection. Because an infection ultimately is a reproduction of that organism to the point where it's causing a problem. Now, I suppose you could have a very large organism like a worm or something that can be pathogenic, and just the one organism, even if it can't reproduce, can be a problem. But for microorganisms, having some of those organisms there, but they can't reproduce, there's no problem. It's not even an infection at that point because it's not propagating. So an infection, which is where we come to the term of disinfection, right? An infection is when you have enough organisms where they are pathogenic and causing a problem. So, for example, even though I just filled this up from the water fountain, and presumably that water should be pretty clean, there's probably a bunch of viruses that might infect bacteria or algae, not humans, in that water. And for sure, I didn't clean and wash this bottle this morning, so it's been at least some time. For sure, I've drank out of it, and some organisms that are in my mouth are now in here, and whatever else happens to be there. And yet, I'm telling you, there's millions and millions of microorganisms in here, and it tastes great. So we kind of take it for granted sometimes, or might do well to consider the fact that just because something's living in there doesn't mean that's bad for me. So we're going to talk about that today. Sterilizing is something we do if we're, let's say, doing a very, very careful laboratory experiment, or being very, very careful with medical equipment that we're going to use, and we just want to make sure there's absolutely no chance something living can get to somewhere where we don't want it. So a sterilizer would look something like a pressure cooker is one way to do it. If we get the temperature high enough, you'll take all of the proteins that form DNA and stuff and give them so much heat that they transform. And so the proteins will denature and you'll kill it. So you've probably heard of like boil water advisories. That usually does a very good job denaturing proteins, but if you want to make absolutely sure we actually put up the temperature higher than 100 Celsius, where you boil water, all the way up to 120 Celsius approximately, and keep it there for some amount of time to make sure everything gets really, really baked. And then at that point, you can be pretty confident that there's nothing else remaining. There are some other ways to sterilize, specifically sterile is what I'm talking about. You can use gamma radiation and things like that. So there's of course many ways to do it, but we usually don't use that type of an approach for disinfection. Now, boiling water, yes, we wouldn't ever do that for like a water treatment system because it's so expensive to produce that much heat. And by the way, just a little side note, if you've ever done any cooking or heard about it, if you go up to high elevation and you try to use boiling water, or you're even cooking something that has to go to a certain temperature, the difference in atmospheric pressure actually changes what's happening because water will boil at a lower temperature, so you'd have to boil for a longer time. And if you're baking something, that's going to change the dynamics of all of that. So kind of a little side note there. The pressure and the temperature is important. Okay, so disinfection. Really, our definition is we have to remove enough of things that could be pathogenic, could cause an infection, to below an infectious level. So when we disinfect the water here, maybe there's a few pathogens in there. But as long as that's not enough to make me sick, then I'm okay. As long as we can be pretty sure of that, then I'm all right. So that's the deal. Okay, so just going to check in where we are with a typical water treatment system. We've talked about most everything now up to this disinfection. And so typically for a disinfection reaction, we will do it in a plug flow reactor. So a lot of the stuff we've done so far has been in these CSTR type systems. And that kind of makes some sense. If we're doing like that coagulation, we just have to get it all mixed. And then a flocculation, we want the particles to meet each other, and that's sort of the point of it. It makes sense to have a lot of mixing in both those scenarios. Disinfection, however, we want to just take some amount of bacteria and reduce that number as far as we can, and that works really well if we take the non-mixed approach. Because if we're mixing what's coming into our disinfection chamber with what's going out, then there's automatically going to be, as soon as something comes in, part of that's leaving. And that means we'll have a higher concentration leaving, typically. Whereas if we just take it along this conveyor belt type of thing or through the pipe, there's no more mixing between the front and the end, and the math works out a little better for us. So if some of these were a CSTR, our disinfection is almost always plug flow reactor. Of course, we could scheme up a little system, maybe something for a campsite or something or do a comparison of a CSTR versus a plug flow reactor. So I'm not saying we'll never see it, but in general, the plug flow reactors are the way it works in practice. And then we send it out to distribution. And that's actually an interesting part too, because a distribution system needs to at least protect the water as it is delivered to my water bottle. And in a way, we can consider that as part of the treatment plan. And typically, we'll actually leave intentionally some residual disinfection in that system to make sure that as it's coming out the fountain, there is some minimum threshold of chlorine typically remaining. That way, any bacteria that might be in the pipes will be prevented from regrowing, repairing, or any of that. Okay, so one key aspect about disinfection, like we said, was we have to make sure that they are not at infectious levels. Well, what does that mean? This calls back to the quote, I forget who it was, the dose makes the poison. So if you know anything about poisons or anything like that, if you have a tiny, tiny amount of it, it's no big deal, right? You could think of the same for almost any pharmaceutical or drug or anything like that, right? If you have a sip of an alcoholic beverage, you're not expecting that to do anything to you really, practically. If you had way too much, then clearly there's going to be some effects. It's the same for poisons. It's same concept here for our disease-causing organisms. If you have just a tiny bit of them, in some cases, there's no problem at all. Either your body's natural stuff is going to take care of it, or they're just never going to get enough hold. But it kind of depends on the species. So, for example, if you've ever had what we often call food poisoning, and I hope none of you have, but probably it's unfortunately relatable. This is actually probably food infection. Could also be water technically, but that's not so common here. Food poisoning, properly termed, is when some poison was in your food. Not a bacteria, not a virus, a poison. Maybe a bacteria produced that poison, and typically if you ingest poison, you have an immediate response. So if you eat something and immediately you're having severe problems, that's food poisoning, to be really technical about it. Food infection is more often what we talk about when we say, I had food poisoning the other day. That's you eat something and some hours later, or maybe the next day, you get sick. You're not quite sure if it was, lunch or dinner, but it was probably that lunch at that sketchy place. You kind of knew something was off, and then you started feeling bad 8 hours later. Something like that. Those are food infections, and that's colloquially we call it food poisoning, whatever. Okay, these are the food infection sources then. You could have a virus, a bacteria, or a parasite, as we often call them, or a protozoa. So a virus, something like norovirus, this is a pretty common one. You've probably seen it in the news. This typically takes like 8 to 12, maybe 24 hours to produce the infection. And it's basically a terrible night or two. Usually a 24-hour ordeal, and then you're starting to feel better. It only takes something like 10 to 50 viruses to get you sick. So these are pretty resistant to our stomach acid. There doesn't have to be a ton of them. And once they're in your system doing their disruptive thing, they're making a lot more viruses. And this is going to go back to what we talked about, kind of introducing the whole concept of water and wastewater treatment to put those two barriers between the fecal and oral route of transmission, right? Anything being excreted by a warm-blooded gut might have pathogens like this. Well, when you have an infection, you're producing billions and billions of pathogens. Those will be released to your wastewater, and therefore we try to keep our wastewater treated. Rotaviruses are quite similar. I don't remember exactly for poliovirus, but polio is also, much like the norovirus and rotavirus, a gut pathogen. In rare cases, poliovirus also caused more severe issues, paralysis kind of stuff, so that's why we take it quite a bit more seriously. But if we control our sanitation, it's almost a non-issue. Okay, so it doesn't take many viruses to get you sick, at least for the norovirus and rotavirus. Bacteria are a bit different. If you've heard of Vibrio cholera, you've probably heard of cholera at some point. This is a species of bacteria that's actually often inhabits kind of naturally some sort of brackish seawater kind of areas. And we're going to talk more about it today because there's some interesting case examples of how we learned about waterborne diseases in the first place. But this one, it's not so fun, but it takes something like 10 to the 6, so 1 million, maybe even to something like 1 to 10 million cells to get you sick. The reason is because it's really, really susceptible to acidic environments. So your stomach has typically a pH around 2. Your body's producing hydrochloric acid, and that's sitting there ready to digest your food. So when a cholera bacteria gets in there, there's a very good chance it's going to die. Now, if you have a full stomach and not a lot of acidity or something, and you ingest a lot of them, chances are enough will get through and then can produce an infection after your stomach where there's less acid. So that's the deal with cholera. Takes a whole bunch of them, and so because that's one that you could get from eating raw oysters, my recommendation is if you're ever going to eat raw oysters, you do it on an empty stomach, okay? And perhaps add a nice dose of some lemon juice or lime juice or something to add a little extra acid to the system. Couldn't hurt. Unfortunately, the noroviruses are not nearly as vulnerable to the acidic environment, so just eat them at your own risk, because those will also, the oysters tend to like filter feed, and viruses and things just kind of stick to their flesh and then preserve them decently well. And you put them on ice, keep them nice and preserved. So there is an inherent risk of eating raw shellfish because of the fecal-oral route of transmission, right? Okay, so you do so on an empty stomach. I actually had a chance this summer, the first time I ever had raw oysters, and I was like, well, if I'm gonna do it, yeah, I'm gonna add vinegar, the kind of little sauce they had, and it's a good thing I'm hungry. And no problem, so that was good. All right, E. coli, you've heard of this one. E. coli is one of these that can also produce a toxin. So there's a couple things that can be dangerous with E. coli. One is that, of course, if it gets to the wrong spot in your body, it can cause an infection. Even though we probably have a lot of E. coli in our guts, it's pretty common to have E. coli. We just don't want it in the wrong spot, right? Kind of the lower intestine is probably the right spot. The small intestine and the duodenum, that kind of stuff is probably the wrong spot. So if they're growing in the wrong spot, then it's the infection. Well, they can produce a toxin, and so if you just have them growing in the food and then you disinfect the food, if you heat it or something, and the toxin isn't degrading, you could have food poisoning. More likely, I think the most common is for the bad cases of E. coli is you get the infection and then they start producing a toxin inside you because it's a particularly nasty strain of E. coli. So the kinds we might have naturally don't typically be are not typically the toxin producers. So it can be a toxin producing one that's making you sick, as well as just propagating in the wrong spot. So I think these are more like 10,000 cells would be required to get you sick, something on that order. Salmonella is pretty similar to E. coli. It's kind of the same deal. A couple of them also can produce toxin. Then the protozoa, these guys are larger organisms, not large like I'm holding in my hand right here. If this is a bacteria, like 1 micrometer, then a protozoa is maybe like this. And the difference is they are eukaryotic. So if we remember from biology, they have an authentic cell wall, like a robust cell wall, and they can close up tightly behind that wall and protect themselves from chlorine and the environment and even heat to an extent. So these are sturdy. They're difficult to kill. They're easier to filter because they're larger. So we'll just say larger and harder to kill generally. At least with things like a chemical or heat. They're actually pretty susceptible to ultraviolet light. And it only takes something like 1 to 5 cells. So even though they don't propagate as much, they're not quite as fast and as quick to multiply as these bacteria cells that just have a lipid membrane instead of a full cell wall. It's not hard for them to get you sick. So if you are exposed, there's a pretty good chance they'll make it past your stomach acid and into your gut and cause a problem. So the bigger question in all of this is, how do we know? How would you design an experiment to figure this out? 5 viruses for you and 5 crypto for you, right? How do you do that? So it turns out the CDC, I assume that they would still do this if they needed to, but for some time they would take volunteers and probably young, healthy people, like, college students needing a few bucks, and they'd be like, "Hey, you want to come do this experiment? We'll pay you $1,000, and you can stay in this hotel, all expenses paid. It's a nice, fancy hotel, hospital, not hospital, it's a hotel, I promise. And then we're going to give you all the food. We're going to control your food. You can't bring your own food because we need to control that. But we'll feed you, and you'll have Wi-Fi and a TV, and we'll just take care of you. And you might get sick." And then you give them like they give some dose, and the dose might be a placebo, so just a little sugar pill, if you're lucky, or it might be some number of one of these pathogens, right? And they're going to provide all the medical care. Obviously, it's kind of a hospital, kind of a hotel sort of situation, and you just kind of take a gamble, and maybe you get a low enough dose where you're not susceptible. Maybe even if you did get a big dose, maybe you're asymptomatic. That can also happen. And then they'll monitor in addition to your sick, whether or not you're sick, asymptomatic cases, you'll still have the infection. It's just not affecting your body. And so you'll still be shedding viruses in your excrement or pathogens, whatever. So they'd monitor all that. Might be a little invasive, but for $1,000, would you take that gamble? This was probably 20 years ago, so maybe $2,000 today. Would it be tempting? Some of you maybe not. Depends on how recently you've had a food infection and how miserable that was. It's a pretty funny thought to consider. Like, how do we know? And any of you definitely yes? Oh yeah, some of you. Free food for a week, yeah. That's great. Well, some of you are like, well, I eat raw oysters anyway, right? So, okay. So how do we know, or like, what's the history of disease? The study of disease. This is a guy named Jon Snow, and it's not the Game of Thrones guy, not that one, right? So it does have the H, so it's not the guy who knows nothing. And I wish I could say I'm from this lineage, but he didn't have any children, so maybe it would be one of his brothers or cousins or something. Perhaps I'm related. I don't know. But some English doctor sort of guy. Maybe I should dress like that someday, and starting to get the receding hairline. Maybe in a few years. We call Jon Snow here the father of epidemiology because he was kind of the first guy to really recognize, hey, it's this water making people sick. And the way he did that was by mapping who was getting sick and comparing that to what water source people were using. So there was an infamous cholera outbreak in the 1850s in London. And ultimately, the story goes, it was traced to one particular well pump. So we'll talk about that in a moment. But this was kind of the first confirmation of the germ theory of disease, and the first time we really said, or anybody really said, oh, we're going to map out who's getting sick and dying and correlate that to where the disease is coming from. So at that time, we barely had microscopes capable, or just starting to get microscopes capable of looking at germs. It was not really commonly understood where disease came from. So if you imagine, it's kind of crazy to think, right? That's less than 200 years ago, and we didn't know what made you sick. And cholera in particular was a really, really scary one because at that time, we didn't really know how to treat it properly. So cholera, Vibrio cholera, is a disease where it infects your intestines, and the bacteria produce, as they're multiplying, they start producing, I guess it's probably would be considered a toxin, but they're just producing stuff to cause their surroundings to do what they want in some sense. And what ends up happening is they cause our intestines, which are normally pulling all the liquid from the food we eat and the water we drink, from the mixture that's inside into our bloodstream. So normally, the normal operation of our intestines is to pull water out from our what we're digesting. Well, cholera reverses that. And so it's pulling water from our bloodstream into our intestines. And you can recognize pretty rapidly that's going to give you watery diarrhea, very bad. And the other thing it's going to do is dehydrate you extraordinarily rapidly. And so if you don't know how to stay hydrated under that kind of condition, which thankfully we do today, so cholera is, if you have access to at least a little bit of medical help, cholera is pretty much just uncomfortable, probably very uncomfortable. But if you don't, then you could be dead within the day, right? Dehydration is that serious, and it's that rapid. So back then, you can imagine a family gets sick, and the next day, 7 of the 8 members of that family are dead, and it's horrifying, right? It's utterly devastating. So to not even know where it's coming from, why is this happening? It's that's stuff of horror stories, right? So this is one of these plagues that were all too common back then. We know that sanitation and hygiene were not strong suits either at that time, and as we'll kind of see. Okay, so there's a really nice short book. It's a very easy read called The Ghost Map, and that's kind of based on the map that John Snow made. I'd highly recommend it if this kind of stuff is interesting to you. Like I said, it's very easy. It's a historical fiction in that they put words in everybody's mouths to tell the story as if it was happening and they were experiencing it. We don't have that detailed of a record, so it's fictionalized in that sense, but it's otherwise as true as they could to the documented history, right? So they fictionalized it a little bit, made it very readable, and it's just a nice book. So if that's interesting to you, here's the black and white version of the map that John Snow made, and this is a sector in England. And if you look at the map closely, you'll see all these streets and everything, and then you'll see these black bars. Let me find my cursor and I'll okay. So you'll see like these black bars sitting there. Well, it's called the ghost map because basically there was a bar drawn for every death in that home. Okay, so you see in these certain spots, some houses had quite a few deaths, some just 1 or 2, and so he did this trying to figure out what was going on with this outbreak of cholera. One of their theories at that time was, hey, maybe it's this miasma, which is the word they gave to like this gross odor, like just stench, and maybe you can imagine like maybe a morning fog, like it's just grungy, just gross looking and smelling, and in the air you just could tell it's bad quality air or something, right? That's kind of what one of their theories. But what he noticed was, well, even in the nicer neighborhoods weren't really, I guess, quite like that. There were still people dying. It wasn't controlled to just these miasma-rich areas or whatever you want to call it. And instead, eventually, he was actually looking through a microscope, trying to see from one of these, I think it was a water sample, trying to see if there was any indication there. He saw little organisms. Probably he didn't have a microscope small enough to actually see cholera, but it gave him the thought that there was some organism in there that was causing the problem. So he was right in the right direction, even if maybe he didn't quite have the technology to see the right thing. So there's some question about did he actually see them, but at the end of the day, it held true. So if we flip this map a little bit and highlight these bars, you can see the sort of a 3-dimensional portrayal here. You can see all these red bars, these are deaths, right? So again, just considering what's happening to your neighborhood with an outbreak like this, that's so terrifying, right? Then the blue flags here are different wellhead pumps. So we'd have different wells around in the area, and then a hand pump that you could use to pump up a bit of water to take and use for your drinking. So you'll see there's quite a few of these wells around, and one right here is the Broad Street pump. So as we can see, that's kind of the epicenter of this outbreak. And so just mapping it like this and putting the features on here was a huge step in identifying, okay, what's going on. So this is kind of epidemiology in a nutshell. Now, what he did then was he said, okay, we need to take off the handle to that pump. And they did so, and the outbreak stopped. So it was like a really pretty impressive thing that it worked, it fixed it, and came to that conclusion. So what happened apparently was at that well, and these wells unfortunately were not very deep, right? Probably 20 to 30 feet deep. Dig till you find water, put in a little bit of lining, and go from there. Now, this well was right on the edge of a building, and the building backing up to it apparently had a latrine that was contaminating that well. It's probably common in a lot of these, unfortunately. And the biggest problem here, I guess, was that there was a source of cholera contaminating that latrine from that household. Now, apparently, I'm not quite sure how they found this much detail, but there was an infant at that house who had recently moved from somewhere else. The infant arrived probably with the family or something, and the infant had an infection. But the fact that an infant's stomach is not developed like ours are made it so that the infant was not so susceptible to cholera. It may have even survived and lived out his or her life. I'm not sure. But it just wasn't, that reversal of the flow direction was not so terrible in terms of dehydrating the infant. So that meant the infection lasted longer and was a more continual source of cholera for that well. So kind of paints the story of how bad water and sanitation was, especially in the cities, in the 1850s, and kind of is terrifying to think about what that was like to be there, right? Okay, so that's the story in a nutshell. So if you'd like a better telling of it, definitely see that book, but quite morbidly fascinating, I'd say. Okay, so what do we do about it? This brings us to our disinfection strategies. Of course, we also try not to ever link our wastewater and our drinking water in any way as much as we can. All right, so disinfection technologies. There's a few approaches we can take. You, of course, have heard of chlorine, so we'll talk a fair bit about that. Typically, when we're talking about chlorine, we're talking about free chlorine. And what we will describe as free chlorine is, we've had a couple examples already. That's going to be hypochlorous acid, HOCl, which will also be in equilibrium. I'm going to write it over here. So HOCl, we have to deal with a little bit of equilibrium chemistry here. That's going to release the proton H+, and that'll leave us with OCl-. So in this scenario, we have two species of chlorine. Both together is free chlorine. Now, really, we're mostly going to pay attention to HOCl because that's the stronger one. It's about 10 times stronger than OCl-. Now, fortunately, we tend to have more of that if we're at neutral pH or slightly acidic. So we can very easily design our system to have mostly HOCl. That's a very important thing to do, and that's our free chlorine. Now, there's a few ways we might add our chlorine. One would be to take chlorine gas, Cl2 gas. It works really well, and it actually adds a little bit of acidity to our system, which is kind of convenient, but it's pretty hazardous, right? Handling gas phase chlorine, if anything goes wrong, people can get severely hurt, if not killed, in operation. So we can take Cl2 gas and dissolve it, react it with water, and we will end up getting some Cl-, which is not reactive. That's chloride. Chloride doesn't do much, just like sodium chloride, the table salt. The Cl- is just doesn't react much. Okay, so we don't really think too much about that. But we would also get HOCl, that free chlorine, And if you count, now we have the two Cl's accounted for, we have an H and an O accounted for, and we need one more H, right? So we have one H plus added as well, which is acid. That's acidity. Okay, so we can get HOCl from that way. We could also get it from adding NaOCl would work too, or CaOCl2. All of those work. We're adding one form or the other of OCl, and OCl is going to be in equilibrium with HOCl. Of course, that's a OCl minus. Okay, so that's free chlorine. If I ever talk about free chlorine, it's those guys, right? No matter how we get there, it's some form of HOCl and OCl minus. We can also talk about combined chlorine, which is, it's not the combination of those other ones. It's actually when we combine chlorine with ammonia. So chances are good if we have, let's say, wastewater, there's some ammonia there. So anytime we're disinfecting wastewater with chlorine, we're probably going to have a fair amount of chloramines. So combined chlorine is the total amount of chloramines in the water. We don't have to worry too much about this. I'm not going to go that far with the chemistry torture for you. But basically, when we have free chlorine and ammonia in solution, we'll get some monochloramine, so one chlorine per amine group. We can get dichloramine and even trichloramine. So there's all going to be equilibrium reactions there. We'll have some mixture of them. And the only important thing I want to say here is these are slower acting, kind of like OCl minus. So these are slower. That means we often will use them for a residual effect. Now, they are also stinkier. So they smell bad. And in fact, if you've ever gone swimming in a swimming pool, and you're like, oh, wow, they used way too much chlorine. Actually, what you're smelling is a lot of chloramines. You don't really smell the free chlorine too well, the strong stuff that actually is cleaning the pool. If you're smelling the chlorine and it's burning your eyes, probably means somebody's either been sweating too much in the pool, releasing a lot of urea and ammonia, or peed in the pool, releasing the same stuff. So that means you end up getting this combined chlorine, and it's unpleasant, right? Not to mention the unpleasant thoughts of where it might have come from. I guess it's also possible that whatever water you used to fill the pool might have had some ammonia. Okay, at any rate, so you've had some probably experience with chloramines, even if you didn't want to, but they can still work as a disinfectant. It's just going to be slower. Probably not something we'd use for the design of let's kill it all in this batch and send it along its way. More so that let's keep a residual amount to prevent anything from regrowing. Chlorine dioxide is another form of chlorine. It's a bit different. The chemistry, we don't have equilibrium chemistry for that one. It's approximately as effective as free chlorine, and not going to say too much else about it. I think it would also have to be applied as gas, so it's the same considerations for chlorine gas would apply in terms of safety. So it's actually not used too often, but certainly is possible and sometimes used. Ozone is another one. This is something, of course, we have ozone in the upper atmosphere where we want it. That's the ozone layer. We also have a bit of it here at kind of ground level, and that's more of an irritant. It's like an air pollutant is kind of how we treat it. And the reason it's an irritant is because it's a pretty strong oxidant. So it can react with stuff and cause our lungs a little bit of trouble. But we could apply it on purpose and use that to give some bacteria some trouble, right? Because most of these are going to be in some way attacking the molecules on the bacteria or the virus. So ozone would do a pretty good job at that. It's sometimes used. There's another thing we can do with ozone is an advanced oxidation process and create some really, really reactive things, jumping ahead here, and often combining that with UV light or something to cause the ozone to split apart into these really reactive radicals. That's typically a little beyond disinfection, although it would disinfect. It's more like we want to get rid of pharmaceuticals or something like that from the water. How do we just blast it with as much firepower as we can. So I'm listing this one here. I'm going to say this is like high firepower for let's say destroying molecules, organic molecules. And whatever else might be there. So this is not necessarily disinfection for the advanced oxidation process, but it kind of puts these together. Okay, so ozone could be just used by itself, or we can make it fancy. UV light is another thing we could use just by itself, or we can make it fancy in conjunction with some other stuff. Actually, some of my research recently has been to use UV light with chlorine and make chlorine fancy. So there's some combinations here if you do some photolysis, splitting the things apart and making them really reactive. But by itself, UV light also works pretty well. And in that case, instead of checking the dose, we talked about dose makes the poison. Well, the dose makes the disinfectant too. For chlorine, you could say we've got, let's say 10 milligrams per liter of it, and maybe there's a relationship between like how much chlorine and how long you give it. So 10 milligrams per liter, maybe 5 minutes is enough. Or you could take 1 milligram per liter and then 50 minutes and would be enough, right? So there's a trade-off there. Even if you do your own household cleaning and you take some bleach and you spray it on something, if you wipe it off immediately, there's a good chance you've not done a lot. So if you accidentally spill some on your clothes and you get it washed off immediately, hopefully you're not ruining the dye on your clothes. But if you put it on there and let it sit there for a long time, that gives it time to perform the reactions you want, or maybe don't want. So if you're going to dye something or do or destroy some dye on purpose to make a cool effect on your clothes or something, you would control the amount of time you're putting your bleach on the spot. So the same is going to hold true for our disinfection. It's going to be a first order reaction, as we'll see. Okay, and all that to say, the same is true for UV, except instead of the dose in terms of a concentration, we would just dose it in terms of how intense is that light, right? We could have a very bright white light, or we could have a very, like a candle light is a very small amount of light. Could be the same wavelength, same intensity, or not same intensity, same type of photon, just have more of them for a bright light, right? So the amount of light is important. We will also talk about later the wavelength that can actually destroy DNA is also important. So we'll come back to that later. Okay, so back to free chlorine. I already said HOCl is the stronger one. It's about 10 times stronger. Let's see. And we then want slightly acidic conditions, because when we have some acidic conditions, that means we have more H plus in the solution. And if we have more H plus, it's going to push that reaction to the left, right? So when we have if H plus is large, then it's going to push the reaction that way, because we have more of the reactant, so to speak, going from right to left. That's actually, we would call it the products, but so if we have more products, it'll push it towards the reactants, I guess we could say. So if we have, let me rewrite this for you. If we have lots of acidity, then the reaction favors HOCl. Okay, does that make sense? And we can remember from our equilibrium chemistry that we can define some equilibrium constant, and we can define that as the products. So in this case, H plus times OCl minus. These are going to be the products multiplied by each other. If we had some some number here that would become an exponent. I'm not going to make you deal with that, so we'll keep it pretty simple here. It'll be these products divided by the reactants. And I think we'll see an example in a moment. For chlorine in particular, under typical conditions, the value should be 10 to the minus 7.54. So that means that if we look at the ratio at some particular pH, we can find that ratio given that equilibrium constant. And we could also even take a moment and think when there's an equal amount of OCl minus and HOCl, that's when it's not just equilibrium. We can be at equilibrium with a different amount, but if we have the equal amounts set HOCl equal to OCl minus, this 50-50, then that's 1 over 1 or 2 over 2 or whatever it is. That term becomes 1. These guys, I'll erase this in a moment to make it clear. But if we set those to equal, that becomes 1, and then we can say at what pH does that happen? That's the pH where the H plus is equal to 10 to the minus 7.54. So that means the pH is 7.54. So there's a neat little trick here just to say that if we know the pKa for the system, then we know at what pH are these two species equal. So I'm just going to say if HOCl is equal to OCl minus, that's a 50-50 split, then the H plus is equal to 10 to the negative 7.54, and pH, remember P is the negative log of H in this case, pH then is 7.54. So given some acidity constant like that, or equilibrium constant, then we know if it's dependent on pH, on the H plus like this, then we can actually very easily know at what pH are they the same. Okay? So just a bit of a reminder, a bit of an elaboration on what we've done before. So let's take an example then. If we have 15 milligrams per liter of HOCl, it's added to potable water, that's drinking water, for disinfection, and the final measured pH is 7.0, what percent of HOCl is not dissociated? It says assume this temperature, and what I'm going to say is if we look it up in a book, then our equilibrium constant is approximately 10 to the minus 7.54. Okay, the question is asking what is the percent of HOCl that is not dissociated? What that's referring to is the amount that is still in the HOCl form compared to the total. And we're going to have to do it on a molar scale because we're dealing with a chemical reaction. So I'm going to give you a few minutes, see if you can tackle that. Technically, we learned this stuff earlier, so this is going to be reviewing what we had brushed up on a few weeks ago. See if you can do that. Did you get an answer? You got partway through, or how'd that feel? You okay with it? If this was a test, you okay with it? See some questioning looks. Maybe not, but close maybe. No response. Okay. So I wrote part of what you'll need here. And the question actually gives us a slight bit of a red herring. The question is asking what percent is in one form or the other. That actually means we don't need the exact concentration. Now, you could go with the exact concentration and then go back and calculate the percent, but we're just going to be dealing with a ratio of the two, of HOCl and OCl minus. And so while you might have thought to go ahead and convert this into molar units, that's probably good practice. In some cases, you might have to do that. Let's say if we added, if the question was asking for something different, maybe you need to do that to see what amount precisely was HOCl. But we can actually find the percent without doing that. So I'm not gonna dive into that part of it. Instead, what I'll say is we're gonna have essentially two unknowns with the HOCl and the OCl minus. We know that the H+, that's given, and whenever we have two unknowns, we need a system of two equations, right? And so one thing that'll help is just to write up any equations that you have, that you know. One of them could be that the total, you could simply write the total amount of chlorine is going to be HOCl and OCl minus. And so I went ahead and used that here, plugged it in so that I had one equation here that relates, this is the answer that I'm trying to get, right? The answer that I'm looking for is whatever is equal to HOCl divided by HOCl plus OCl minus. That's ultimately what I'm looking for. The second equation would be my equilibrium equation, which says my K is equal to the product of the products over the product of the reactants. So meaning H plus times OCl minus divided by HOCl in this case. So that's a second equation that I have some information. And then I just need to find a way to combine the two. So what I will do next is take this HOCl divided by OCl minus plus HOCl, simplify that a little bit, and I'll say, bring this down here and say, if I divide the top and the bottom by HOCl, I'll be left with 1 over 1 plus OCl minus divided by HOCl. That still is essentially going to give me the answer that I'm looking for. So now the question is, how do I do some sort of substitution for HOCl and OCl minus? Really what I want to substitute it in is for things that I know, right? And that's where I'm going to get the KEQ here from. And if you look at this equation, it's pretty simple to find a substitution just if we divide both sides by H plus. Right, so if we divide it KEQ by H plus, then what we're left with is OCl minus divided by HOCl. This exact pattern is basically what we use to solve almost any of our equilibrium equations if we have to go this route. Sometimes you'll just have the values and you can plug them in, right? Maybe you don't have two unknowns, but it's quite convenient because then we can plug that in here and say the answer that we're looking for is going to be 1 over 1 plus, and instead of the OCl minus over HOCl, I'm going to put in KEQ, K over our H plus. And now we have parameters there that we know. Okay, and I didn't calculate that yet, so if, oops, sorry. feel free to get there before I do, but I'm going to pull up Excel and put in those numbers. Okay. Let me know if you get the answer. And we're at pH 7, so that's going to be 10 to the minus 7. Did something wrong. Let's do that. Okay, so the answer becomes 0.776 or 77.6%. If we stop and think about it a moment, the question is asking how much did not dissociate, meaning how much of the HOCl did we have left? We are slightly more acidic than the pKa, where it's 50-50. And so if we've gone acidic compared to where they're 50-50, and we have more protons around, that's favoring more of the compound with H in it, because we're feeding it more H, so it reacts and we get more of the HOCl. So we're feeding it the H plus when we're moving down the pH scale, more acidic. So we're getting more HOCl, so that means we should expect that it's at more than 50%. But we're still close to the 7.5 mark, so we're not too far from 50%. If we were to do the same calculation at pH 3, it would be close to 100% is HOCl. That's kind of the deal with the log scale here. Okay, how is that? Do you feel a little better about it now? Okay. Good news, if you just really hate chemistry, this is the last kind of bit of chemistry that we need for the class, kind of. So if you can manage this or manage to get most of it, you'll get by. You'll be all right. Okay. With that, that's it for today. Oh wait, I'm sorry. I must have hit the blank button. Okay. I'll give you a little bit more. We still have a little time. So I apologize I got your hopes up, so I'll make it quick. And then we'll pick up. We won't do that next problem here. We'll start there next time. Okay, so one other thing about chlorination, if we use way too much chlorine, there's a potential problem in that we can accidentally create what are called disinfection byproducts. So we can actually create hazardous chemicals with whatever random organic material that happens to be there. You know, let's say plant leaves decay and add a little bit of a stain to the water. Certain functional groups, certain pieces of the chemical there can react with the chlorine and then form things like trihalomethanes, haloacetic acids. Certain classes of molecules that we know are either carcinogenic or kind of toxic. And generally they're going to be in small amounts, but we monitor for them and watch out for them. And if things go poorly and we use way too much chlorine, or we just have way too much of this natural organic matter stuff, which really is random assortments of all sorts of molecules. Like, there's no way we're dealing with all of that precise chemistry. Even analytical chemists are not precisely describing all of what's in natural organic matter. But we can monitor for some of these. So if we have too much of the organics and we're overdosing because we didn't design our reactor properly or something, then we get in some trouble at levels where it might be a true hazard. Again, dose makes the poison, so if we have a tiny, tiny bit of it, it's kind of expected and probably below what we could detect, and that's not going to harm anything. Okay, the way we design our dosage for disinfection is on the basis of our mass balance. Okay, a mass balance in terms of the number of bacteria that are there and how effective is chlorine against that particular organism. So we tend to define this term called CT, the CT concept, concentration of our disinfectant times the time that it has to contact it. That's just like the example I said with the bleach on the countertop. If you spray it there and leave it for 5 minutes, that's a lot different than spraying it and wiping it off in 5 milliseconds, right? It's going to have a much different outcome because you're giving the chlorine time to react. So the dosage we would say then is the concentration multiplied by the time. So putting those two pieces together can give us what we need to solve the mass balances that we've been doing. So we'll have a rate at which N, the pathogen, is changing, is going to be equal to, that's the same thing as saying dN dt, right? Is equal to negative K times C to the N power. This C is the concentration of our disinfectant, right? A lot of times we say dC dt. Right now we're doing dN dt. So C is separate. C is the concentration of chlorine or whatever and should not be changing. Raised to the N power, we'll talk about that in a minute, times N, the number of pathogens, the one that is changing, to the 1 power. That means it's first order, right? So the N to the 1 is first order. This looks very much like the stuff we've done before, except we have this extra C in there, which should be just a constant. If we keep things simple, it is just a constant. So N is the number concentration of pathogens, the uppercase N. C is the concentration of the disinfectant. Maybe that's milligrams per liter. The little n, this is a dilution coefficient. If we have an ideal reactor and the chlorine is perfectly well mixed, N is 1, and we don't have to think about it. So just letting you know that we could think about it if, let's say, we had a ozone contactor and the ozone had a different concentration where all the bubbles are going and some of the reactor didn't get those bubbles or something. We might have to deal with it. That's one spot where we would deal with that. But for the purposes of our class, we're going to assume that's 1. Putting all these pieces together and including this coefficient of specific lethality, this whole concept here is called Chick-Watson kinetics. That's for the people that developed this a little over 100 years ago now, defined that, hey, this is how it works. This is how well we can kill things. That K here, this coefficient of specific lethality, it's going to have a little bit of interesting units because we've added that concentration term. So the units are going to be a little different. It should be per time if the only thing that we had here was the change in the number of pathogens. So here with a specific lethality, this is specific to whatever disinfectant we're using and whatever organism we're attacking. We talked earlier about the organisms, how they're different from one organism to another. Well, some of them resist chlorine better than others, so we're going to generally design things for the most resistant, and so we have a specific K that we need to calculate for a given organism. That's specific to the organism and the type of disinfectant chemical we're using. Okay, so this then, if we combine this K with the C, the constant, let's say chlorine or disinfectant, then we get the per time unit that we're typically expecting. So we can do that as a simplification, say, let's assume that's constant, and now we have K star as the combination of the two, and that's going to be in maybe per minutes or something like that. So we can boil this all down to the typical dN dt is equal to negative K times N. Right? We've started here with the class. We know this now. We can do that. And most of the time, that's going to go into a plug flow reactor. There's nothing stopping us from designing a CSTR. It's just probably not as effective for what we need. Okay, talked about the pathogen specificity. Here's just an example from my research some time ago where we were disinfecting some virus. This one happened to be a virus that infects bacteria. It's about the same size and shape as norovirus, so it is a pretty good surrogate for norovirus. And the disinfectant was a material that was producing a fancy form of oxygen called single oxygen, which is highly reactive, and we could see if If we have the different amounts of that, we have different speeds at which it's killing the organism. So we can do these experiments, and we can, in real time, takes a day to incubate them, measure the impact. From there, we can come back and find the K. So I'll pick up here next time, and we'll take a look at that. All right, have a good fall break.